As the global energy sector pivots toward decarbonization, decentralization, and digitization, virtual power plants (VPPs) are emerging as pivotal systems in reshaping grid dynamics. By intelligently aggregating distributed energy resources (DERs), VPPs deliver both energy and ancillary services to the grid through coordinated control. Leveraging advanced communication networks, control technologies, and software platforms, these systems actively monitor and optimize energy flows. The result: enhanced grid flexibility, responsiveness, and resilience. Yet, despite their transformative potential, VPPs face a complex array of operational challenges: grid integration and real-time responsiveness, cybersecurity vulnerabilities, interoperability across diverse systems, regulatory alignment, market access, and participation hurdles. To fully unlock the value of VPPs, stakeholders must embrace robust operational frameworks and adopt proven strategies that ensure technical scalability, reliability, and regulatory compliance. Virtual power plants (VPPs) represent a sophisticated approach to energy management, where geographically dispersed distributed energy resources (DERs) are aggregated and controlled as a single, coordinated power entity. This architecture enables flexible, efficient, and intelligent interaction with the grid and energy markets. Core components of a VPP DER assets include solar PV systems, wind turbines, electric vehicles (EVs), battery energy storage systems, and combined heat and power (CHP) units. VPP Platform, a software-driven system that orchestrates the real-time coordination, optimization, and dispatch of DERs based on grid demand and market signals. Communication infrastructure facilitates seamless data exchange between individual DERs and the central VPP controller, ensuring synchronized operation. Interfaces with grid and markets enable active participation in electricity markets and the provision of grid services, such as frequency regulation, peak shaving, and demand response. Types of virtual power plants (VPPs) can be broadly categorized based on their core operational objectives and functionalities. Commercial VPPs, designed primarily for participation in wholesale electricity markets. These VPPs aim to maximize economic returns by strategically managing energy generation and dispatch. Technical VPPs, focused on maintaining grid health, these systems provide crucial services such as voltage regulation, frequency control, and overall system stability, especially in environments with high DER penetration. Hybrid VPPs mixed models integrate both commercial and technical features to deliver economic value while actively supporting grid reliability. These VPPs balance market responsiveness with operational integrity. Operational challenges in virtual power plants (VPPs), distributed energy resource DER coordination and control. Managing a virtual power plant involves navigating multiple layers of complexity due to the diverse nature of DERs. Key challenges include resource heterogeneity. DERs differ in response behavior, storage capacity, generation patterns, and control capabilities. This variability poses challenges in achieving seamless, unified control across all units. Latency and real-time synchronization. Efficient operation requires tightly synchronized data exchange and command execution. Any latency or misalignment can impair responsiveness and grid stability. Dynamic forecasting complexity. Continuously predicting energy demand, generation output, and market prices is vital but inherently variable. Accuracy in forecasting determines the effectiveness of dispatch strategies and market participation. Grid integration challenges of virtual power plants (VPPs). As VPPs scale and integrate deeper into modern power systems, they present unique technical challenges that must be managed thoughtfully. Grid congestion and stability impacts. The deployment of large-scale VPPs can influence local voltage profiles and disrupt frequency stability, especially in regions with dense DER penetration. Inertia deficiency and system strength. Since most VPPs rely on inverter-based resources, they inherently lack mechanical inertia, a key component in traditional grid stability. This absence poses challenges in maintaining system strength and fast frequency response during disturbances. Interoperability and standards in virtual power plants VPPs. Ensuring seamless operation across diverse energy systems requires robust interoperability, yet several challenges persist. Proprietary protocols and system silos. Many DER platforms operate on closed or non-standard communication protocols, which obstruct seamless integration and limit cross-platform coordination. Absence of unified frameworks. The diverse nature of DER technologies demands standardized, interoperable interfaces. Without such harmonization, system-wide control and scalability remain constrained. Regulatory and market barriers facing virtual power plants VPPs. While VPPs offer promising pathways to modernize grid operations and democratize energy participation, significant regulatory and market obstacles remain. Undefined participation frameworks. In many jurisdictions, existing market designs do not explicitly recognize the role of VPPs. This lack of clarity hinders their formal integration and creates uncertainty around rights, responsibilities, and operational boundaries. Limited market accessibility for aggregated DERs. Smaller distributed energy resources grouped within VPPs often struggle to navigate complex bidding, settlement, and compliance procedures. This restricts their ability to fully participate in electricity markets and deliver value. Cybersecurity and data privacy in virtual power plants. As VPPs increasingly rely on digital connectivity and distributed control systems, safeguarding their infrastructure against cyber threats becomes paramount. Exposure to cyber threats. The expansive digital interfaces and communication layers within VPPs create multiple attack vectors, making them vulnerable to unauthorized access, data manipulation, and service disruptions. Sensitive data protection. VPP platforms handle large volumes of customer-specific energy data. Ensuring privacy and security demands robust encryption protocols, strict data governance frameworks, and compliance with regional cyber regulations. Economic viability and business models for virtual power plants. Despite their strategic promise, VPPs face notable financial and structural hurdles that impact adoption and scalability. Uncertain return on investment (ROI), high upfront costs for deployment, ongoing operational expenses, and compliance-related overheads can outweigh projected benefits, creating hesitancy among investors and operators. Incentive misalignment. Existing tariff structures and pricing models often fail to adequately reward distributed energy resources DERs for their grid contributions, thereby discouraging meaningful participation in VPP schemes. Best practices for optimizing virtual power plant VPP operations. Achieving high-performance VPPs requires a strategic blend of robust technology and intelligent design. Key best practices include integrated communication and control architecture. Deploying resilient and high-speed communication systems ensures reliable coordination across distributed assets, enabling real-time responsiveness. Adoption of standardized protocols. Implementing industry-recognized standards such as IEC 61850, OpenADR, and IEEE 2030.5 facilitates interoperability across diverse DER platforms, reducing integration complexity and enhancing scalability. Deployment of edge computing. Enabling localized decision-making through edge devices allows faster response times, decreases reliance on centralized processing, and minimizes communication latency critical for time-sensitive grid functions. Intelligent AI/ML-based optimization. Utilizing artificial intelligence and machine learning models empowers predictive analytics for accurate forecasting, optimal dispatching, and proactive fault detection, elevating overall system performance. Advanced forecasting and scheduling in virtual power plants. Precision in forecasting and adaptive scheduling is critical to enhancing the reliability and responsiveness of VPP operations. Key approaches include hybrid forecasting techniques. By integrating weather forecasts, historical performance trends, and real-time operational metrics, VPPs can generate more accurate predictions of energy generation, demand patterns, and market fluctuations. Scenario-based scheduling models. VPPs employ flexible planning frameworks that account for best case, worst case, and moderate scenarios. This enables dynamic adjustment to uncertainties, ensuring grid support and market responsiveness even under volatile conditions. Regulatory engagement and policy frameworks for virtual power plants. To unlock the full potential of VPPs within modern energy markets, regulatory reform and inclusive policy design are essential. Key priorities include market recognition and role definition. Energy policies must formally acknowledge virtual power plants as legitimate market participants endowed with defined rights, responsibilities, and operational privileges. This ensures fair access to grid services and market mechanisms. Aggregator enablement models. Regulatory frameworks should facilitate third-party aggregators in pooling distributed energy resources and representing them within energy markets. Such models foster innovation, encourage small-scale participation, and enhance overall market flexibility. Cybersecurity by design in virtual power plants. Embedding security into the core architecture of VPPs is essential to ensure resilience, trust, and operational continuity. Key elements of this proactive approach include secure system architecture. VPPs must incorporate layered security mechanisms such as virtual private networks (VPNs), firewalls, intrusion detection systems, and routine cybersecurity audits. These components collectively safeguard digital interfaces and mitigate vulnerabilities. Blockchain-enabled data integrity. Integrating blockchain technology enhances transactional security, transparency, and traceability across distributed energy resources and grid operators. This decentralized ledger ensures tamper-proof data exchanges and builds stakeholder confidence. Consumer engagement and incentivization in VPPs. Empowering consumers as active participants in energy systems is central to the virtual power plant model. Key strategies include dynamic tariff structures. Introduce flexible pricing models that financially reward users for supporting the grid during peak times or engaging in demand response programs. These incentives foster collaboration between households and grid operators. Intuitive digital interfaces. Deploy mobile applications and online dashboards that allow users to track their energy consumption, monitor financial rewards, and stay informed about their participation status. These platforms enhance transparency, motivation, and trust. Scalable and modular architecture in VPPs. Building flexibility into the digital backbone of virtual power plants ensures long-term adaptability and efficient growth. Key features include plug-and-play integration. Modular design allows seamless onboarding of new distributed energy resources without disrupting existing operations, streamlining deployment and accelerating innovation. Cloud-native infrastructure. Leveraging cloud technologies empowers VPPs with scalable performance, robust fault tolerance, and instant access to real-time data, driving responsive decision-making and system-wide coherence. Global case studies in VPP innovation. Next Kraftwerk Germany. As one of Europe's most expansive VPP networks, Next Kraftwerk orchestrates over 10,000 decentralized energy assets. It actively engages in day-ahead power markets and delivers frequency regulation services using advanced AI-driven optimization algorithms, demonstrating digital agility at national scale. AGL VPP South Australia. AGL's initiative leverages residential solar panels and battery systems to create a robust distributed energy ecosystem. This VPP supports the grid through load balancing services and strategically participates in energy arbitrage, maximizing value from real-time market dynamics. Tesla's VPP California USA. Tesla's solution interconnects residential power walls to enable peak load management, load shifting, and emergency grid response, especially during extreme weather events like heat waves and outages, offering a glimpse into resilient, consumer-led energy models. Future outlook for virtual power plants. The next evolution of VPPs will be shaped by deeper integration, digital intelligence, and global cooperation. Key trends include convergence with smart grid ecosystems. VPPs will increasingly synchronize with smart meters, electric vehicles (EVs), and prosumer technologies, enabling seamless data exchange and dynamic participation across the energy landscape. Catalyst for net zero ambitions. With their inherent flexibility and distributed intelligence, VPPs are set to become pillars of decarbonization, supporting renewable integration and reducing reliance on centralized fossil fuel systems. AI blockchain synergy. The fusion of artificial intelligence and blockchain will empower VPPs with secure, adaptive, and transparent control, redefining how energy is transacted and managed across digital grids. Global harmonization and standards. Achieving scale and interoperability will require unified technical protocols and regulatory frameworks. Realizing the potential of virtual power plants represent a paradigm shift in energy management, offering powerful avenues for grid modernization, enhanced reliability, and clean energy integration. Yet their full potential can only be unlocked by tackling key operational hurdles such as complex system coordination, data interoperability, and regulatory fragmentation. To rise beyond these challenges, stakeholders must commit to adopting standardized communication protocols that ensure seamless device interaction, leveraging AI-driven optimization to enable smart, adaptive control, implementing robust cybersecurity frameworks to protect digital infrastructure, establishing supportive policies and harmonized regulations that foster innovation and scalability. When these elements converge, VPPs can truly serve as transformative pillars of tomorrow's energy ecosystem, flexible, intelligent, and decentralized.